Hi guys, we've been talking about ionic compounds, we've been talking about molecules, molecular compounds that have covalent bonds in them, and today we're going to start comparing the two in terms of their physical properties. So the first thing we want to look at is what does their physical structure look like? So in an ionic compound, we have a whole bunch of cations and anions. They're attracted to each other based on their opposite charges. Cations are positive, anions are negative. So all those ions are attracted to each other to make their physical structure. In a molecular compound, we have molecules that have covalent bonds in them, and we have a whole bunch of those identical molecules, and all those molecules are neutral. When we use the term identical, we mean that they're the same composition and they're the same geometry. So they're all the same type of thing, they're all the same shape, and we have a big collection of those neutral molecules. So what that leads to over here, this is what an ionic compound would look like if we were to put a whole bunch of cations and anions together. You can see the positives and the negatives, they all attract each other, and they end up making this nice, neat, three-dimensional structure. Where over here, this would be a molecular compound. So we have these molecules, they're all identical, they all have the same geometry, and we just have a big collection of those particular molecules. So for the ionic compounds, this structure right here, we call that three-dimensional structure a crystal lattice. And that crystal lattice, when we look at it macroscopically, ends up looking something like this. We can see those crystals have that nice, neat geometric pattern from those ions lining up like that. And most of those ionic compounds we're going to look at are going to be solids at room temperature. Now for molecular compounds, the structures are going to vary. It's going to depend on the composition and the geometry. Their state at room temperature is going to vary as well, depending on what they're made up of. Most of our molecular compounds are going to be gases or liquids at room temperature. There are some that are solids, but not nearly as many as ionic compounds that are almost primarily solids. So you can see over here, this gas, here's what our molecules would look like. Those look like oxygen gas molecules. Now, if we do have a solid molecular compound, there are two different forms of solids depending on what they're made out of. There are crystalline solids, which are these over here. So label B, these are our crystalline solids, and you can see their nice, neat, uniform structure. And then there are amorphous solids, and you can see this right here, this one is A. A is an amorphous solid. You can see that it doesn't have any sort of symmetrical arrangement. It's just kind of a jumble of those molecules. And amorphous means without form. And so you can see there's no defined form in that solid structure. Now with ionic compounds, because of their ions, they're going to have melting points and boiling points and a hardness. Those properties are all going to depend on how strongly the particles are attracted to one another. So in these ionic compounds, the ions are really strongly attracted to each other. And so this ionic crystal right here is going to require a large amount of energy to be broken apart, which means ionic compounds have high melting points and they have high boiling points. So you can see here's our crystal. This one happens to be NaCl. We add heat to it and we can start to make those ions come apart, but it's going to take a lot of energy to make that happen, to melt an ionic solid. The ionic crystals are also hard, brittle, and rigid in their solid form. So what that means is if you have this crystal right here and we apply an external force to it, like hitting it with a hammer, you're going to move those ions, and so like charges end up being next to each other. And we know that things that have the same charge repel. And so that force of repulsion would actually make that crystal break apart. So the brittle and rigid means that if you apply force to it, it breaks. It doesn't bend like other solids could. It would actually crack and break apart. Now for molecular compounds, our molecules have weak attractions between them. So compared to ionic solids, ionic compounds, they're going to have low boiling points and low melting points, which is why a lot of them are found as liquids and gases at room temperature. If they happen to be in the solid state, they're going to have much lower melting points than ionic solids will. And that leads to a lot of the molecular solids being soft or waxy, which means you can bend them or reshape them when a force is applied, where, as we just saw with an ionic compound, when you apply force, they're going to crack. So because of those weak attractions, the properties compared to ionic compounds for molecular compounds are much different. Now, why do ionic compounds have these properties? What gives these ionic compounds their properties? Well, the answer to that is strong attractions between the ions. Those strong attractions are everything when we're talking about these physical properties. And there's a name for this strong attraction. It's called lattice energy. And lattice energy is the energy required to separate the ions in an ionic compound. So it's going to take a whole lot of energy to pull those ions apart. And the greater the lattice energy, the stronger the force of attraction. Lattice energy, or this strong attractive force that we're talking about, is directly related to two things. It's related to the size of the ions, and it's related to the charges of the ions. And we're going to look at how those two things cause this really strong attraction. So first we're going to start with ionic size. When we're talking about the size of the ion, we're measuring it as the radius of the ion. So you can see here's a picture. The radius of this ion would be this distance right here. The radius of this ion would be this distance right here, right? So we're looking at the radius of the ions. Over here, here's our anion. Anions are generally bigger because they have gained electrons. Here's our cation. Cations are smaller because they have lost electrons. And then you can see they have those positive and negative charges. Now this gives you an example of how you can use the periodic table to compare ion sizes. So if you take a look at what we have going on here, this is group 1, so these are all of the alkali metals. Group 2 have the alkaline earth metals. And then we skip the transition metals over to group 13. So here's aluminum right there. Group 14 is carbon. And then when we get to groups 15, 16, 17, you can see these ions are going to be a lot bigger because now we're talking about anions with a negative charge. So these are going to be much bigger. So in our little boxes, you can see the symbol, the ionic radius. So it actually gives you a value for the size of the radius, the charge of the ion, and then the little purple circle, it's going to give you the relative size. Now, if you'll notice, there's a trend in how the size changes as we go down the periodic table and as we go across the periodic table. And if you look at that trend, it shows us that as you go across the periodic table from left to right, the size of the ions decreases. And as you move down a group, because we're adding those extra energy levels, the size of the ions are going to increase. So if we go back, you can see the size of the ions increases as we go down the table, and the size of the ions decreases as we go across the table. So we can compare them in terms of their size by looking at where they are relative to each other on the periodic table. So here we go with our trend. Decrease in size as you go across, increase in size as you go down. So let's look at some examples. Smaller ions form stronger bonds than larger ions, which means they have greater lattice energy. So I have a table here of lattice energy, and you can see it gives you the different compounds and it gives you a value for their lattice energy. The higher the number, the more strongly attracted the ions are to each other. So if we're comparing lithium fluoride with sodium chloride, we know by looking at the periodic table that lithium is smaller than sodium and fluorine is smaller than chlorine. So lithium fluoride has small ions, sodium chloride has bigger ions. And if we compare their lattice energies over here, lithium fluoride has a greater lattice energy than sodium fluoride. So that means the lithium and the fluoride ions are more strongly attracted to each other than, I was looking at sodium chloride over here. Sodium chloride is 769. So lithium fluoride and sodium chloride compare to each other based on the size of their ions. Now the second thing that affects the lattice energy is the charges. Ionic bonds formed from the attraction of ions with larger positive or negative charges generally have greater lattice energies. So if we look at, for example, lithium fluoride, lithium is a +1 charge, fluoride is a -1 charge, compared to magnesium oxide, which is a +2 and a -2. If we look at lithium fluoride and magnesium oxide, we can see magnesium oxide is significantly bigger because of the +2 -2 attraction compared to the +1 -1 attraction. So when we're comparing these things, the charges are going to far outweigh the size in terms of comparing strong attractions. So if you have two ions with charges that are larger, +2, +3, -2, -3, those are going to be much more strongly attracted to each other than things with +1, -1, even if they're smaller ions. So charge will outweigh size when we're talking about comparing lattice energies. And last, let's look at two examples. Which ionic compound would have the greatest lattice energy? So we're looking for compounds with small ions and with big charges. So if we compare sodium and potassium, we know that potassium is bigger in size, so we can rule it out automatically. And then if we're comparing sodium chloride and magnesium chloride, sodium and magnesium are similar in size, but because magnesium has a +2 charge, that one is going to far outweigh the attraction than sodium chloride. So magnesium chloride will by far have the greatest lattice energy of those three compounds. And our last question of the salts below, which would require the most energy to break the ionic bonds, meaning which one has the greatest lattice energy? Well, if we look at B, C, and D, those ions all have +1, -1 charges. But in A, barium has a +2 charge. So because of our charge here, barium chloride will have a greater lattice energy. It will require the most energy to break the ionic bonds. Even though some of these ions might be smaller, that +2 charge is going to make barium chloride the winner in terms of lattice energy. So when we're looking at the strength of these different properties, whether it's an ionic compound or a molecule with covalent bonds in it, you have to look at the forces of attraction. That attraction is what definitely is going to give these things their properties, and we're going to continue exploring these properties in class.